9 part 3. Normally I would not do that to you on a Monday afternoon. I just kind of cut part 2 short, so I needed to catch up on time with y'all. So if you didn't get a chance to watch it, it's there, and I'm gonna do 1 or 2 problems like that. Then we'll go from there. Let's see. So this is not in your PowerPoint, it's just a problem out of the back of your book. Number 60. And the end of chapter 9. If you looked at what I posted yesterday, this problem's actually a little bit easier. All right, so in part 3, I talked about using this relationship. Q of one substance equals negative Q of the other substance. Okay, it's just like the delta E of our system is always equal in magnitude, but opposite in sign to the delta E of our surroundings. The reason that is because the delta E of the universe must remain constant. So if I need it, I'm going to take it from one of the other, okay? So I can apply that same thing to heat if I'm talking about a thermally isolated system, okay? So in this case, I am. So we can say that iron is our system, water is our surroundings. And so they're only going to exchange heat with one another, okay? Anytime you put two objects together that are at different temperatures, heat will flow from hot to cold until thermal equilibrium is reached. That is just the final temperature for both materials that you're talking about. Okay, so I could plug in what we know Q to be. We know that Q equals MCAT, or mass times specific heat times delta T. So I can plug that in on both sides of my equation and then plug in the corresponding pieces and solve for the mass of water. Okay, so let's do that. I'm going to come over here and do it. All right, so what I'm using. So if I substitute in my Q formula, it's going to be the mass of iron times the specific heat of iron that I've got to go look up, times the change in temperature of iron. I could also write that as TF minus TI, final minus initial. Anytime you see that delta symbol, it's final minus initial. Okay, now I'll do the same thing to the other side, but don't forget your negative. And it doesn't matter which side you put the negative on, it'll always work out to be like it's supposed to be. All right, I need iron and waters. What is it? 0.41. And water is 4.18. Okay. Right, my units. All right, now just go plug everything in. Mass of iron. Specific heat of iron. Final temperature, which is 59.5. Minus initial temperature of iron was 22.7 equals the negative mass of water, we don't know, specific heat of water, final temperature of water, again, is 59.5. Then the initial temperature of water was 63.2. Okay, now to start simplifying. I can completely simplify this left side to one thing. Then on my right side, I'm gonna multiply delta T and my specific heat, and then I'll be left with the mass of water. So it's kind of like your X. Make sure you do your temperature change first, then do your multiplying. I'm not rounding anything just yet. I'm gonna hold out to the end. Okay, so on the right-hand side, when I did my delta T and my specific heat, I got a negative number. But don't forget, we have this negative out here in front. So these two negatives are gonna make it a positive. Now I'm just gonna divide both sides by that 15.466 grams joule cubic. I got 34.7 grams. That's my mass of water. Any questions about the math, the algebra, the formula? Okay, I'm going to go ahead and erase the problem and write another problem, but I'll leave that up for just a second. All right, now I'm going to do number 62 out of your textbook. This one is more like the ones that I did yesterday. Hey, y'all take a minute or a few minutes and try to work that out yourself. And then I'll do it. Let's see if you can do it. They don't turn the air on, I'm gonna go on strike. All right, there's everything plugged in for you. See if you can go from there.
Okay, I'm going to start working it, but I'll explain it after I get everything up here. Working it step by step, just so you know exactly what I've done. There's more than one way to simplify this. So if you didn't do it my way, but you still get my final answer, that's completely fine. All right, so far I multiplied my mass and my specific heat together on both sides. So I did 2.85 times 1.28, and I got this number. Okay, did the same thing over here, I got this number. Now I'm distributing this number to both of my temperature terms. So it goes to the TF and my initial temperature. So when I do that, this is what I get and my corresponding units. Did the same thing on this side, but I also went ahead and distributed my negative. Okay, now I need to get like terms on both sides. So I'm going to add 31.559 to both sides. Move it over here, because those are my two TF terms. Then I'm going to add 3.75, blah, 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 to both sides. Move it over here, because those are like terms. Right, so let's see what we get from there. Okay, so now that's what my equation looks like. Now the only thing I have left to do, divide both sides by 31.9238 to get TF by itself. At 51.8 degrees Celsius. That is the final temperature of both objects at thermal equilibrium. Any questions? Just remember your algebra rules. All right, so this is about as hard as the problems get in this chapter, and it's really not hard. You're good at algebra. Okay. All right, so that is how we calculate Q. What is our other part of our energy equation? Work. Now we need to talk about how we calculate work. So remember our delta E equation, our heat plus our work. So we just found, or not just, but you know, we found that we can find heat using our MCAT equation. Now we need to look at how we find work. The only work we're going to talk about is pressure volume work. A gas. So pressure volume work is just the work caused by a change in volume against some external pressure. Your external pressure needs to be held constant in order to use the equation. Okay, so the work equation for pressure volume work is negative. I'm going to negative is part of the equation, so don't forget. Negative pressure times delta V. Delta V, final volume minus initial volume. So for units, your pressure always needs to be an atmosphere, and it will always be given to you in atmosphere because we haven't talked about different pressure units. That's in chapter 2. And your volume needs to be in liters. So when you get your work, it'll be in units of atmosphere time liter. That doesn't work. Why doesn't it work? Because Q is always in joules, as is energy. So if I'm adding Q and W together, they need to be in the same unit. So the hardest part about calculating work is remembering that you've got to convert it to joules. So to convert to joules, 1 atmosphere time liter is equivalent to 101.3 joules. Right, so all of this is in your PowerPoint that I posted last week. So next up on the PowerPoint is example 9.4.
Okay, so it says to inflate a balloon, you must do pressure volume work on the surroundings. All that means is your work is going to be negative. If you inflate a balloon from a volume of 0.1 to 1.85 liters against an external pressure of 1 atmosphere, how much work is done in joules? All right, well, let's just plug it in. Work equals negative pressure, which is 1 atmosphere, delta V. So my final volume is 1.85 liters. My initial was 0.1. Okay, so I do my delta V. And multiply it by 1, it's the same thing. So I get negative 1.75 atmosphere times liter. I can't leave it like that, so I need to convert it to joules. If I want atmosphere times liter to cancel, I'm going to put 1 atmosphere times liter on bottom, 1.103 joule on top. Atmosphere times liter cancels. When I put it in my calculator, I get negative 177.275 joules. Obviously, that is not proper sig figs. If I did proper sig figs, it'd be negative 177. Easy peasy. It looks like most of you have your laptop so you can access, or you should be accessing the PowerPoint. I'll give y'all just a second to look at the for practice 9.4 and the for more practice 9.4. If you don't have something to look at it with, ask your neighbor to share with you, and then I'll give you the answers. All right, next thing is calorimetry. There are 2 types of calorimeters. I don't know why we haven't brought in an eraser. Okay, so there's 2 types of calorimeters. One is constant volume. So if I'm trying to find the change in energy of a system, and I'm putting it in a constant volume calorimeter, my work becomes 0, right?
because it can't change its volume. So volume is 0, that makes the whole thing 0. So at constant volume, your delta E is just your heat associated with whatever process you're undergoing. Well, if it's only heat, then we only need to look at our Q equation. And we've said that if my system and surrounding are isolated from the universe, then my system heat is equal to the negative of my surrounding heat. Well, in this case, we're going to consider our surroundings as our calorimeter. Because it's isolated from the universe. We actually have a bomb calorimeter. I don't know if it works. It's in 312 where you go for freedom. So in other words, I can find the heat of my system by using the negative heat of my calorimeter. That's pretty easily done. It's easily done because the only thing you have to measure is your change in temperature. So for every calorimeter, you have a heat capacity. That is not the specific heat capacity. It is just heat capacity. So you don't see a mass in this equation. So it's heat capacity times delta T. So all I have to measure is the change in temperature of this process, and I can figure out how much heat is associated with my system. Okay, well, unfortunately, since our bomb calorimeter doesn't work, I'm not going to spend a lot of time on constant volume calorimeter. Instead, we're going to talk about the calorimeter we use. Where is it? Next week in lab, we're actually going to do an experiment with the coffee cup calorimeter. So this is a constant pressure, so constant volume. But before we can talk about it, I have to introduce a new thermodynamic function. Hour and 15 minutes seems like the longest compared to 50 minutes. All right, so we have a new thermodynamic function. It's called enthalpy. The enthalpy is the heat evolved in a chemical reaction at constant pressure. It is abbreviated with the letter H. All right, so enthalpy we represent with the letter H of a system is defined as the sum of its internal energy and the product of its pressure and volume. So if I were to write that as an equation, it would be H equals E plus P times V. But there are several state functions within this. Enthalpy is a state function, energy is a state function, volume is a state function. Remember, state functions just mean you are only concerned with final and initial, not how it got there. All right, well, if I plugged in this, what my energy we know now to represent, would look like that. Q plus W plus P times delta V. There, you should look at it and say, delta V, P times delta V is very similar to work, but work has a negative in front of it. So what happens to those two terms? They cancel. So delta H is just equivalent to Q.
Would it be a negative Q because you still have the negative left from the work?
Yeah, so let's plug it in. So it'd be Q instead of we can do plus. Negative P delta V plus regular P delta V. So those two just cancel. So enthalpy is very convenient because most of the time we're only concerned with heat change. We don't really care about the work being done. So with a constant pressure coffee cup, what you're actually finding is your delta H because it's at a constant pressure. Right, so when we go to do problems dealing with a coffee cup calorimeter, it's what we were doing at the beginning of class today. Basically, we put a reaction into this coffee cup. We measure the change in temperature. Well, normally I think next week we'll do acid-base. We do an acid-base reaction, but it's in water. So we measure the change in temperature of water, and then we find the heat of our reaction. Okay, so unlike the Bond calorimeter, you're still using your MCAT equation. Okay. So really, you already know how to work these problems, just didn't know you did. So that is where I will stop and we will pick up on Thursday. If you wish to only come one day a week, talk to me about that. If you want to come every day, you don't have to talk to me about that. Just come every day. Y'all have a good week. Don't forget about lab stuff.